up, you guys? Yes, welcome back to another PY212 review video. I'm Seven.
I'm Mark.
And I'm Roger.
And today we're going to be talking about AC circuits and transformers. Let's go!
All right, guys. So for AC circuits, one of the most important concepts to understand is impedance. So impedance, we have this formula for it. What's all this mean? So impedance is made up of two components. That is resistance, R, and reactance, L. So resistance comes from our resistors, obviously. And the value of that resistance is just going to be equal to the resistance of the resistor. Big surprise. But reactance is a bit more complicated. So we have two types of reactance from our two other electrical components. We have inductive reactance, XL, and capacitive reactance, XC. So our inductive reactance is going to be equal to omega times L, and our capacitive reactance is going to be equal to 1 over omega times C, where in this case, omega is the frequency of our sinusoidal signal from our AC generator. So what we can see here is that they sort of have an inverse relationship with omega, right? As omega gets bigger and bigger, the reactance of the inductor is going to get larger, whereas as the frequency gets larger, the reactance of the capacitor is actually going to get smaller. So how do these all combine into impedance? Well, it's going to be equal to this expression. Why this expression? Well, let's turn over to our phasor diagram. So on our phasor diagram, we're going to draw these reactances as phasors on the phasor plane. So R is going to go horizontally, XL is going to point straight up, and XC is going to go straight down, which I forgot to label. But this is XC. And so when we want to find the total impedance, which is the combination of the resistance and the reactance, we're going to do a vector sum of all of these vectors. So XL and XC, since they're pointing in opposite directions, we're just going to, they're basically going to cancel out. You're going to be left with one vector pointing either up or down. And that's why we have XL minus XC here. And then our resistance R is just going to be pointing out this way. And then in order to do the vector sum of two perpendicular vectors, you just do Pythagorean theorem. So we have the magnitude of R plus magnitude of R squared plus the magnitude of the reactance squared, which of course is the difference between the inductive and capacitive reactances. And then we're going to square that, and we take the square root of all of those in order to get the hypotenuse of Z. And that's going to tell us the size or the magnitude of our impedance vector. So we know the magnitude of Z. What do we do with that? Well, the cool thing about impedance is that the unit of impedance is actually in ohms. So what that means is we can actually apply Ohm's law with impedance instead of resistance like we did for DC circuits, which means that we have that our max voltage, and remember, because this is a sinusoid, it'll be changing over time, but we take our maximum voltage is going to be equal to our maximum current times our impedance. So as you can see, we can find out the relationship between these if we can get our impedance. And then, of course, we can write sort of the inverse of this, where Vm over Z equals Imax. So these are really useful for finding out different sorts of relationships between voltages and currents in AC circuits. And because Z is actually determined partially by omega, we know that at different frequencies, we'll actually be getting different voltages and different currents for given voltages that are oscillating at different frequencies. Okay, so now let's apply what we've learned about impedance to an actual circuit. Here we have an AC voltage generator, a resistor, a capacitor, and an inductor all connected in series. And so we can draw all of our resistance and reactance vectors, you can see drawn here in blue, and sum them up into our total impedance. Now, another thing we can do to find out the relationship between current and voltage in this circuit, we'll draw our current vector going to the right, and then our voltage vector is going to go in the same direction as our impedance vector. And that's really important, because what that means is that our voltage and our current are not always going to have, they're not always going to be in sync, because what this phasor diagram actually represents is that the horizontal component of these current and voltage vectors are what you're actually measuring on the circuit. So we want to imagine that both of these vectors, the red ones, are rotating counterclockwise at the speed of the oscillations of our generator. So this will be rotating at omega radians per second. And as they're rotating, we're going to be looking at the horizontal component of the vector. So if we imagine this rotates 90 degrees up this way, we're going to see that I is going to be fully vertical, which means we're not going to measure any current at that instant, but our voltage is going to keep the same angle. So if I is fully vertical, our voltage is going to be a little bit to the left, which means we're going to measure a very small negative voltage. And as we continue rotating them around, our voltage and current are going to basically trace out a sinusoidal graph over time. However, because we have this small difference in the phase, we're going to have a desync in where the peaks and troughs of those graphs are going to be. Okay, so now let's look at a few different phasor diagrams for a few different situations. So let's start over here. Here we can see that the inductive reactance is bigger than our capacitive reactance, which means our impedance vector and thus our voltage vector is going to be pointing up. So when we start rotating this counterclockwise and plotting the horizontal components, we're going to get a graph that looks like this. Here we can see the current in green and the voltage in red. And we can see that the voltage is going to be leading the current, which means that as we look at our graph, we're going to hit our peak voltage before our peak current, peak voltage before peak current. So in this case, we say that this is an inductive circuit because there is a more inductive reactance, which means that our voltage is leading our current. Here, we're going to see that we have a more capacitive reactance. We have more capacitive reactance than inductive reactance. And so our impedance and our voltage are going to point downwards. So as we start rotating this counterclockwise and plotting the horizontal components, we'll see that our voltage is going to start lagging our current. So here we have a current peak and then a voltage peak, a current peak and then a voltage peak. So we're going to say that this circuit is capacitive because it has more capacitive reactance and a voltage lagging the current or current leading the voltage. And in the middle here, we have that the capacitive and reactive, the inductive and capacitive reactance are equal to each other. So our impedance and voltage are all lined up on the horizontal axis. So as we start rotating this, our peaks and our troughs are going to line up perfectly. And this is a special type of situation which we call resonance. And resonance is important because it gives us this lined up current and voltage. So one special thing about resonance is that we want the reactance of the inductor and the reactance of the capacitor to be equal to each other. So we know that inductive reactance is omega times L, and capacitive reactance is 1 over omega times C. We can rearrange this, and we can multiply by omega C on both sides. We get omega squared LC equals 1, and we do a little bit more algebra, and we find that omega equal to square root of 1 over L times C. So this is a really important equation to know, because if you are given a certain capacitance and inductance in a circuit, you can find out what the resonant frequency of that circuit is. Or if you're given a certain frequency on a generator, you can find out what sort of capacitance and inductance you need to have in order to hit the resonant frequency. And you might also notice that this frequency, that this is similar, or actually exactly the same as the oscillating frequency of our LC circuit. And that sort of makes sense, right? Because if you have an LC circuit, that wants to oscillate at a certain frequency. So if you are supplying it with that exact same frequency from a generator, you're basically leaning into those natural oscillations, and that's going to give you the most amount of power and the most amount of voltage and current. Now let's try all that out in a real problem. So here is problem 5 from your discussion worksheet number 11. We have this circuit here. We have a AC voltage generator with a max voltage of 10 volts and 250 radians per second, omega. And then we have a capacitor with 1 millifarad, a 4 ohm resistor, and a 4 millihenry inductor. So first we want to calculate our resistances, reactances, and impedance. So you can see I did it all out right here, use all the formulas we had from before, and we end up with an impedance of 5 ohms. So you can check this against your work, but it's just a simple plug and chug with the equations that we have. And then we want to find the maximum current. So very easy, we just use Ohm's law, but with impedance instead of ohms. So I max is equal to the max voltage over the impedance, 10 volts over 5 ohms, 2 amps. Easy peasy. And now we want you to find the voltages over each of the electrical components. But again, this is really easy because we know the current and we know the impedance of each component. So the impedance of a resistor, capacitor, or inductor is basically just its resistance or reactance. Because impedance is this formula here, if everything else is 0, like if you have no resistance and no capacitive reactance, then your impedance is just your inductive reactance. Or if you have no capacitors or no inductors, then your impedance is just your resistance. So in this case, we can just plug in our resistance and reactance as our impedance, and we can solve that the resistor has 8 volts, the capacitor has 8 volts, and the inductor has 10 volts. Or that's the max voltage they're going to be at. If you notice, these all add up to more than 10, but that's because these voltages are going to be happening at different times. So at any given time, they'll add up to 10, but at their max voltages, these are what they're going to be. And we can actually graph that on our phasor chart here, and we can see that we have our VL pointing up, our VC pointing down, and our VR pointing to the right. And then with this, we can also plot our max voltage on this phasor chart. And we'll notice that this max voltage is actually going to be going below the horizontal with a certain angle phi. And this angle phi is really important because this helps us calculate our average power. So our average power is going to be equal to 1/2 times our max voltage times our max current times the cosine of this angle phi. But how do we find that angle? How do we find its cosine? Well, remember our good old friend SOHCAHTOA. So the cosine of this angle is going to be equal to the horizontal component divided by the hypotenuse. So our horizontal component is our resistance. So our resistance is going to be equal to 4 volts, or 4 ohms, sorry, and our horizontal component is going to be our impedance, which is going to be 5 ohms. So this is just 4/5. So
Hey guys, it's Roger in the edit, and I just wanted to clarify something from the video I thought was a bit confusing. So this angle phi that we're looking for here is actually the angle between the current phasor and the max voltage phasor. However, we can't use SOHCAHTOA on current and voltage because in order to use it, both quantities need to have the same unit. So because current is in amps and voltage is in volts, we can't divide them in order to find that angle. What we can use is resistance and impedance because those are both in ohms. So I have here drawn all of the voltage vectors or the voltage phasors that we drew before, and now on top of them I'm going to draw the reactance and resistance and impedance phasors. And you'll see that they all actually perfectly line up with their voltage counterparts. So we'll see that the inductive reactance is in the same direction as the inductor voltage, capacitive reactance is in the same direction as capacitor voltage, resistance in the same as resistor voltage, and impedance in the same as max voltage. So because these are all in ohms, and I want to find this angle here, I can actually use SOHCAHTOA on the resistance and the reactance in order to get the value of that cosine, which is the exact same as the cosine of the angle between the current and the voltage maximum. I also could have done the resistor voltage max and the total voltage max, but I just wanted to make my life more complicated, I guess. All right, back to the video.
plug all of our values in, 1/2 times 10 times 2 times 4/5. And that is going to all equal, 20 is 10, and 4/5 is 8 watts. And there you go. So now let's move on to the last 4 parts of this problem. First, it wants us to find the resonant frequency of this circuit. So as we figured out before, that frequency is going to be 1 over the square root of LC. Plugging in all our values, we're going to get that omega is 500 radians per second. And now, because our frequency change, we're going to have different reactances in our capacitor and inductor. So we can recalculate those. Again, the exact same formulas as before, and we get 2 ohms for each of them, which means when we calculate our impedance, these two are going to cancel out, and our impedance is just going to be equal to our resistance, because it'll be resistance squared root of that. So it's just a resistance, which is 4 ohms. So when we look for our max current, we're going to get our max voltage over our impedance, and now our impedance is 4 ohms, so we're going to get 2.5 amps, which is more than the 2 amps that we had before. And when we look at our phasor diagram, we'll have that VL and VC are going to be the same length, so that Vmax is going to point fully in the horizontal direction, which is going to line up with I. And so when we go to find our average power, we'll plug in the same formula as before. Now phi is equal to 0 because Vmax lies in the horizontal plane, and so there's no angle. So our cosine 0 is 1. We'll multiply 10 times 2.5, which is our maximum current, and we're going to get 12.5 watts, which is way more power than we had before. And that's why understanding resonance is so important, because if you hit a resonant frequency in your AC circuit, then you're going to get the maximum delivered power.
Okay, guys, let's look at a transformer problem, specifically problem 4 from your discussion 11. And so what's going on in this problem is we have an AC voltage source, like a wall socket, and this voltage is going into a device called a transformer. And what this is, roughly speaking, is 2 inductors where they are kind of communicating with each other. Specifically, you feed in a wave oscillating signal here, you get another oscillating signal in your other inductor. And the difference is you get a different amplitude of that voltage signal on one side of the transformer compared with the other. So you're transforming the amplitude of your signal. And once you have the desired amplitude of your voltage signal on this side of the transformer, you can power a device with that, which in this case we're just going to model as a resistor with resistance R load, right? And you have some sort of voltage across this resistor and some current flowing through that resistor, and the power dissipated in that resistor is what we're going to call the power delivered to our device. Okay, now what we want to start is, if we know the RMS of the input voltage, which is from our wall socket, 120 volts, we know that. Well, how do we know what the RMS of the output voltage is from the transformer? That's what we want here. Okay. And the way we're going to do that is we're going to do the following. So if we consider our output voltage, so where is that actually coming from, right? Why does this transformer do what it does? Well, the reason is we have changing current through this inductor. That changing current creates changing magnetic field, both inside and outside the inductor. That changing magnetic field creates a changing magnetic flux through your other inductor, and that induces your EMF here, and that EMF is your output voltage. Okay, and so V out, we can also write this as epsilon out, if it helps to think of this as an EMF. And this is given by the number of coils in your output inductor, so N2 here, times the change in time of the flux delivered to your inductor 2 from inductor 1. And the way we denote that is with this 1, 2 kind of thing, right? So this is our Lenz's law. We know that. What about our V in? So we know what V in is, but we can also relate this to the current going through this part of the circuit. And we just recall the definition of inductance for that. And we can say, without worrying about any minus signs, okay, because we only care about amplitudes here, we can say that this V in is given by L1 times the rate of change of the current through that inductor. Okay, and so now let's take these two expressions and let's see what we get when we plug them in here. Okay, so we get something like N2 d phi 1 2 dt L1 di1 dt. And you can see that L1 and N2 are constants. So what we can kind of do is get rid of the ddt in both the numerator and denominator. Makes it easier to look at. So let's do that. Okay. So, in this combination of symbols, we can recognize something called the mutual inductance between our two inductors. Specifically, this equals M12 over L1. And this is because M12, by definition, is given by this expression. Okay, and so all of this is to say that the ratio that the transformer applies to your amplitude is given by the ratio of the mutual inductance to the self-inductance of your first inductor. Okay, and without going through any math of what these are in terms of, number of coils, area in your inductor, all that, we can just say that for a perfect transformer, this ratio is given by the number of coils in your second inductor divided by the number of coils in your first inductor. And if we put this all together, what we see is that V out RMS over V in RMS equals N2 over N1. Okay, so now I'm going to erase some of this because now we can actually answer part A of this question. Okay, so this is the result we got by going through kind of physically where these come from, our V out and V in. But now that we have this result, now we can say that part A is asking for the ratio of the coils, N2 over N1. And by the way, we can use the proper language here and say that this is N secondary over N primary. And so what we want V out RMS to equal 12 volts. Right? That's what the problem wants us to do. V in RMS we know is 120 volts. And so that tells us that N secondary over N primary is equal to 12 over 120, which is 1 over 10. And so what that means is that we want more coils on our first inductor than on the second. Okay, that's question 1, or part A, sorry. You can label this as part A. Now let's look at part B. Okay, for part B, we want to know what current, RMS current passes through our 2 inductors. And the way we're going to find out what this is by physically thinking about the power or the change in energy going from this inductor to this one. And so the assumption for a perfect transformer is that all the change in energy from this inductor due to the changing magnetic field stored in here, it's either staying in the circuit here or it's going to this inductor. So there's no energy kind of leaving our system here. And so what that tells us is that I1 RMS times V in RMS, that's our average, if you want to think about change in energy through our inductor. Not really power like for a resistor, but very similar idea. So the change in energy through that inductor 1. If that energy is changing, that means it's going to our second inductor. And so we can set these two quantities equal to each other. And that tells us that, again, V in RMS is 120 volts. V out RMS is 12 volts. And the other kind of piece of information we want here is our R load. So specifically, whatever current is being generated in this inductor here, it's passing through this resistor, our load, and power is being dissipated in there, which is equal to our I2 RMS squared times our load resistor. Just our standard I squared R for a resistor. Okay, now our R load is 6 ohms in this problem. We can also write this as I2 RMS, V out RMS. Right? This is just our IV formula, which is the same as I squared R for our resistor. And so this actually tells us, by comparing these two, what that I2 RMS equals, well, let's divide through here a little bit. We get V out RMS over 6 ohms. And using this piece of information, we can do the following. We can substitute. We can say that this is V out RMS squared over 6. And now we can find I1 RMS. So I1 RMS. Let's substitute V out RMS we know is 12 volts. So that'll be 12 squared divided by V in RMS, 120, and also divided by our load resistance. And so we get 12 squared over 120 times 6, and that should give us 0.2 amps. now that we know this, we can come back to our original equation here, and we can also say that I2 RMS is V in RMS over V out RMS times I1 RMS. And this ratio here is 10, as we know. And so we get 2 amps for our average current delivered to our device here. Okay, and that is part B. So, okay. Part B, 0.2 amps, 2 amps. Okay, now let's move on to part C. Part C is kind of just a continuation of part B, where we found the RMS current delivered to our device. We said that I2 RMS was 2 amps. And for part C, we want to know the average power that is being delivered to our device here. And so that is just the power being dissipated in our load resistor, which is kind of I squared R, except that we need to make sure to use RMS. And so our load, we remember, is 6 ohms. And so we get 2 squared times 6 is 24, and the unit is watts. So this is the average power being delivered to our load. Finally, in part D, we're asked to think about what happens if, instead of our input being on this side of the transformer, what if we were to switch things around and have our input be here and our device be on the left here? And so what happens is that the ratio of our V1 to V2 doesn't change, because that's a property of our transformer. Right? So we said V1 RMS over V2 RMS. Initially it was 120 volts over 12 volts, which is a ratio of 10. And that ratio will stay the same even if we have our input on the other side of the transformer. And so if instead of 12 volts output, we have a 240 volts input, so we are asked to consider V2 RMS equals 240 volts. And so now, instead of knowing V1 and wanting to find V2, we know V2 and we want to find V1. And so using this ratio, we can say that V1 RMS is going to be 10 times V2 RMS. And this, again, this 10, it's a property of transformer. This does not depend on where the input or the output, where the device, where the power supply is. And so, since this ratio is constant, we say this is 10 times 240. We get 2.4 kilovolts root mean square voltage now on this side of the circuit. And this is a very high voltage, lethal, so that would not be a good idea unless it's super duper safe. Okay, that's problem 4 for you guys. Hopefully that was good, and yeah.